Hello, all. Welcome back from the break, and I hope you had a great morning and learned a lot about how to use NetworkX. Here, we will introduce a particular use case where we use NetworkX to analyze Sumerian documents. Yeah, welcome.
I'm Adam Anderson. I've been working with the data discovery program for a number of years, and especially excited to be a part of the project with Niek and the team of discovery students working on Sumerian network analysis.
My name is Niek Veldhuis. I am professor of Assyriology here at UC Berkeley, and I am the PI of the Sumerian Networks project.
My name is Yashila Bordag. I'm a fourth-year data science student and also a student developer on the SumNet team.
My name is Coleman Bowden. I'm a fourth-year applied mathematics student, and I'm also on the SumNet team.
All right, and today we're going to be talking about network analysis of ancient Sumerian texts. In particular, the Shu archive of Pusrish Dagon from the dates between 2100 and 2000 BC. In this demo, we will use NetworkX to help solve a riddle contained in a small administrative archive of cuneiform tablets from the ancient Sumerian city-state of Pusrish Dagon, known in modern times as Drahem in Iraq. The archive contains many records of the production of fine shoes, along with precious metals and gems. But why does this small collection of 300 texts exist among thousands of administrative records? To help answer this question, we use network analysis in order to map the relationships between the actors of this small archive and visualize the social network to find the leaders and their cliques in the archive as a whole.
So we'll start with showing you how the data is transformed from a piece of clay with cuneiform on the left all the way to the right, where you see a simplified graph of the actors in this particular text. So the first step is to digitize the text, that is to transliterate it into a romanized form and then to enter it in a computer file. The second step then is to lemmatized this text. Lemmatization means to connect each word in the Sumerian text to an entry in the Sumerian dictionary. And then finally, the proper nouns, royal names, personal names, and deity names are pulled out of that lemmatization and put into a graph to the right. We'll go into a bit more detail about each of these steps right now. First, about the tablets. These tablets were found in a site that was called Pusrish Dagon in ancient times. Today the site is called Drahem, and that is in the deep south of present-day Iraq. That site was active as a royal archive between 2060 and 2000 BCE approximately. Some 15,000 tablets are known to come from the site of Pusrish Dagon. The great majority of those were looted from the site. They were not excavated, but they were looted and sold on the black market. And that happened primarily between the end of the 19th and the first half of the 20th century. What it means is that these 15,000 tablets today are spread over museums and small collections all over the world. We have a good number of them here at the museum on campus in Berkeley, but you will also find them in musea all the way in New Zealand or Australia and every place in between. The great majority of the texts from Drahem or from Pusrish Dagon deal with animals. These animals are owned by the king, they are given to the king, or they are given out by the king. but this is personal property of the king. Among all of these tablets, we also find a smaller archive that we call the Treasure and Shoe Archive. And there are approximately 300 tablets that we know about today for this archive. And those are the tablets that we will be working with today. The digitization and lemmatization process is done on a site that is called the Open Richly Annotated Cuneiform Corpus. ORAC provides standards and tools for the transliteration and lemmatization of cuneiform text. Each tablet is assigned a unique ID number, and the data and metadata can be downloaded in JSON format, and then it can be further processed in Python or R or whatever you want to use. The lemmatization of all this data is performed by scholars in the field. So the lemmatization was already done before we started this project. And how that works, you can see on the right side. You get a line of transliteration, followed by lemmatization, followed by English translation. So Tugar Kubabar Ten Ginta in lemmatization becomes Gar is a ring, and that is a noun, and Kuk Babar means silver, and that is also a noun, and Ging is a unit, and that is also a noun. We pull out the proper nouns from the lemmatization, and then we look for keywords in the text to see what is the role of each proper noun. The first proper noun that you see in bluish green there is Ninsumonak, and Ninsumonak is marked as a god by the extension DN, meaning deity name. Shusuen then is marked as RN, meaning royal name, so Shusuen is the king. And then finally Ludingerak is marked as PN, a personal name, so he is just a proper guy. Now Ludingerak is preceded by key, and key is one of those keywords that we use. Key means that the rings in this case are expanded by Ludingerak. Shusuen also has a keyword. The keyword there is Arua, meaning offering. These rings are an offering by Shusuen to Ninsumonak. And in this case, Ludingerak is sort of a middleman. He is the one expanding the rings, but Shusuen is ultimately responsible. And that gets us to the directed graph on the right, with two arrows, one from Shusuen to Ludingerak, and one from Ludingerak to Ninsumonak.
In practice, we do this rule-based generation using pandas data frames in Python notebooks, and we generate two different data frames, the nodes data frame and the edges data frame. In our nodes frame, we have a line for each node that we want to use in our graph. And in this node, we have the lemma, which is the word which we have identified as the actor in the transaction in the text. And with this is associated a set of metadata, such as the translation, transliteration, part of speech, and other attributes which we have associated with the lemma, as well as the role of the actor in the transaction, and a couple of attributes which would be other keywords that have been associated with this particular node in the text. Together, we can see that in the nodes frame, we have Ludingerak as one row, and Ninsumonak as another row, and that we have identified different attributes associated with this node. We will use this to populate the node attributes in the NetworkX graph in our demo. Next, we have our edges frame, which includes the data for the edges. And here we have directed edges, which identify the source and target depending on who has been identified as the source in the text and the recipient in the text. And we also see what kinds of edges these are, meaning whether they were transactions or relationships. And also we see where the text was coming from in terms of the tablet number that we see under ID text. Finally, the weight is associated with the number of such transactions that we found associated between these two individuals. And with this edges frame, we can construct the NetworkX graph.
So with NetworkX, we're able to construct a visualization of the resulting graph. So the idea here is that we are able to see the main players in this network by size and color. Larger and brighter nodes are larger players based on degree and eigenvector centrality. Additionally, the idea here is to have the nodes spaced in such a way that you can see even what the smaller players are doing. Like if you track with your eyes one particular node, you should be able to see who they're connected to. So the end result is something that allows you to see the overall structure of the graph and like how the important players relate to each other while also seeing fine detail.
So now we'll jump into the demo. So yeah, so now we can download the notebook, which we will be doing the demo through from our GitHub page. This is the link, the bit.ly link. And so here, to download it, we can go to the raw file. And if you hit Control S, you can save the page as a Python notebook locally onto your computer so that you can run it locally, or if you want to use Google Colab, which is what we generally use for our work, you can then upload it here. And in Google Colab, if you right-click here and go to Open With, then you can open Collaboratory. And through here, you can essentially like collaboratively work with other people who might want to run like the same Jupyter notebook as you. And yeah, so you can basically share your work pretty easily. Much of this like initial text is stuff that we've already gone through. If you are interested in learning a little bit more about our node and edge harvesting methods, you can visit the same GitHub repository again, which is linked here. And as a basic overview for how we will be going through this tutorial, we will initially be setting up the libraries which we want to use and also downloading the data. And then we will talk a little bit about how we approach visualization and then do some fun analysis. This notebook will mainly be using NumPy and Pandas. And our data can be read pretty much straight from like the GitHub from the GitHub repository that we put up. And if we look at like the two data frames as we saw in the presentation, we can see that the edges data frame has like the same format. And then here we're selecting for the few columns which we think are going to be relevant for our later analysis. There are more columns, but they mostly have to do with the lemma and some metadata about like the particular form that the lemma is taking. And so yeah, next we will be building the graph.
Okay, so now we actually get to the part of the tutorial that uses NetworkX. So the first step is to construct the graph using NetworkX. So we're going to need to import NetworkX as a first go. After this, we have the edges in the edge list frame, and they're already in the correct format for NetworkX to import them. So it has a default command for that from pandas edge list, at which point we end up with a graph with nodes and edges with the properties ID text, weight, and edge type. But we still need to add the properties of the nodes to the graph that we have from the nodes list or nodes frame. So in order to do that, we use the nx.setNodeAttributes function. And this will take a dictionary. In this case, we use nodesFrame.toDict and apply the values of that dictionary as variables of the node that the key represents. So after doing that, we also would like to have the degree as a property. You can actually get the degree from an object from NetworkX, but just for ease of use, we also like to have it as a property. Okay, so in order to visualize the graph, we're going to first need to import matplotlib. This is what NetworkX uses in the drawGraph function, which is how we draw graphs with NetworkX, if you can believe it. So in order to draw a graph of our order, which has over like 100 nodes, we're going to have to think about it a little bit and be kind of careful because it's very easy to sort of have an overload and everything is just super cluttered and you can't get anything out of the visualization. So the first step in that is sizing the nodes. Because the nodes are more or less connected or are more or less important to whatever feature you're investigating, it's beneficial to size nodes that have a greater magnitude in whatever property you have, larger, and conversely, less magnitudinous nodes smaller. So that's where node size calculator comes in. We input our graph, a property name. So this is just one of the properties of the nodes that we already defined above, a min size and a max size. So let's just define that. Okay, so that's step one, done. Next, we have to figure out how we're going to position the nodes on the graph. In order to do that, we're going to have to think about the nodes and the edges holistically. Because if we have a lot of nodes in the center or a lot of edges crossing each other, that's harder to read. And naturally, a graph this size is going to have some edge crossover. But we want to minimize that as much as possible. We also want nodes that are more closely connected to be closer together, just because it allows a quick sort of visual analysis of who is talking to who. So NetworkX has a default algorithm for determining position of the nodes on a graph visualization. It's called Spring Layout, and essentially the way it works is that the edges act like springs, attracting the nodes they're connected to, and the nodes have sort of an anti-gravity that repels one node from another node as they get close together. And now there's just the question of actually drawing the graph. In this case, we define the node sizes. We want some pretty colors to provide further visual information for the end user. So we do that here. And again, we specify just by attribute name to allow it to be as flexible as possible. That's sort of really the benefit in this instance of the attributes. You can swap them out from one another, define a new one based on old ones, and then use that, and then that information is stored and attached to the node forever. We have the labels, which is a slightly less involved calculation than the other two. We're just going to move them a little bit up from the node that they're attached to. Pretty easy. And so then comes the drawing of the edges and nodes. You can draw them all at once with NetworkX.drawNetworkX, or you can do it like we're doing here, which is where you draw the nodes first because we have node positions, and we can define a lot more fine parameters for how we want to do that. And then we draw the edges again, defining the parameters a lot more specifically. And then we draw the labels. And after that, we're essentially done drawing the graph. Just draw a little color bar so we can see what's what. Okay, so now that we've done all that, we're ready to actually draw the graph. So here's a drawing of one that we already ran. We can also redo it and see what new sort of results it gives us, because this is, non-deterministic. Takes a little while to run, but once it pops out, it's interesting because it looks pretty similar, except it's, it's rotationally, like the symmetry of rotation uh, is invariant with respect to like multiple runs. So you can, it's just as likely for Ludingerok to be at 0 degrees as it is for Ludingerok to be at 90 or 91.725. But the actual structure of the graph seems to be fairly well preserved across multiple runs, aside from that rotation. So one of the really important things, especially for a graph like ours, are measures of centrality, which is essentially how important this node is in the context of the graph as a whole. For our purposes, we're going to mostly be focusing on eigenvector centrality, which is essentially a way of balancing out the nodes such that nodes that are connected to other nodes that are important themselves, and then, sort of they reach an equilibrium. So we calculate these metrics, and then we add them as properties to the nodes for a graph, because why not? And this, again, really helps with ease of use later on. So the next step is just take a look at what sort of results we get. So this is a histogram of the eigenvector centrality. As we can see, there's actually, of course, a few extremely important people, but there's this kind of strange gap at around 0.07. So we're going to be looking at what the nodes above this gap are like, because these seem to be like the important people. And it's interesting that there's actually a fairly large distinction between the two. You can easily create a subgraph in NetworkX just by, giving a list of the nodes of the subgraph that you want to generate. So in this case, we just check to see if the node is with eigenvector centrality greater than 0.07. And this is what we get.
All right. Thank you, Coleman and Yashila. As you can see, we've made some exciting new discoveries thanks to our talented data science discovery students. So we're looking now at the results of eigenvector centrality in a subgraph. Eigenvector centrality usually represents a leadership score. The question is, now that we see this focus on a select group of individuals from the treasury texts, the question remains, who are these people and why are they in this subgraph? To understand what we see, we need to think of this as a map of hubs and authorities dispersed across the of Draham, the site of Draham itself, and the city-states that extend throughout the region. And these can be seen both spatially and temporally. But in this representation, they're just shown in terms of who is interacting with whom. And that is where the arrows are coming from. So to illustrate this, let's start in the middle of our graph with Lugal, which means king in Sumerian, has the highest eigenvector centrality. And although this term is representative of the crown and the royal palace for a period of 28 years. So that means that it represents many kings, from Shulgi to Amarsin and Shusin and Ibisin. So there's 4 kings in this archive, at least. Next, we then can look at Ludingerok, who is the top treasury administrator between the years of 2041 to 2034. So for 7 years, this individual is administrating in the treasury here, and is clearly a central hub with all of these arrows pointed inward for the most part. But he does redistribute a lot of the precious metals, shoes, and hides to different individuals, as we see. Next, we have Lugal Kugzu, who is a top internal administrator as well from the years 2051 to 2025 BC. So he's around for 30 years, the longest career that we see among these officials, if indeed it's all referring to the same person. So in this case, we see Lugal Kugzu receiving and sending a lot of the commodities that are counted in this group of texts. And we'll get into some of the details as well. For example, Puzur-Era is another top treasury administrator, and from 2053 to 2043, for about 10 years, he is doing the kind of similar functions. His kind of receiving some of these metals and leather, and then distributing them to people who are further out. So for example, Dada is in this archive attested for 11 years. He is a Sharabdu, an administrator as well. So there's kind of an administrative circle here. Lunana, although somewhat common name, Lunana is attested here for 17 years and has a number of titles over the course of that time. So he's first a Shabra, an administrator, then he's a Nubanda, then he's an Ugula. So both of those are levels of overseers. And then he is a Dikut, or judge. And if indeed it's the same person, then we see over the course of 17 years, the kind of progression of this man's career. Then we have Dayanum Mishar. He is the top administrator for the weapons from 2053 to 2038 BC for about 15 years. He is in charge of all of the weapons coming in and out of the treasury. Next, we have Ululal, who, as you can see here, delivers weapons to Dayanum Mishar. So this is one of the people who is receiving weapons from Puzur-Era and delivering them to Dayanum Mishar. Ayamu delivers weapons to Sagdana in Nippur. So at least that's what he's doing in this text. So again, kind of a part of the weapons delivery that's recorded in the treasury texts. Ayamu is attested for 21 years in the Drayam texts. So also someone with a long career. So Dada, as I mentioned, was the Sharabdu administrator and is in the archive for 11 years, attested. Lisin is the a Giri kind of conveyor of goods, someone who's delivering. In this case, in this archive, he's delivering a bed to Ludingara. And he is kind of a deliverer for the space of 19 years. Then Utamisharam, kind of an interesting individual. He's more or less a processing agent, if you will, from 2052 to 2027, about 25 years, beginning in the end of the reign of Shulgi and going through to the beginning of Ibisin. So really long career for Utamisharam. He's in charge of the disbursement of animals, both small and large, to the leaders and centers around Drayam and elsewhere. So for example, he'll receive animals that are meant to go to the kitchen, and then he'll send animals
for dedicatory purposes, and then he will get the hides when they've been slaughtered and send them elsewhere. So he's kind of a someone who deals with the processing of animals. Then we have May Ishtaran, who Utamisharm is closely connected with. She is a princess of most likely Amar Sin. The years in which she's attested in this archive are 2046 to 2027. So for 19 years, we have May Ishtaran, and she is doing a number of different things, usually working with precious metals in terms of giving and receiving them from the treasury. Next, we have Shu Enlil, who is the son of the king, most likely Shulgi, and so he would be a prince. He is attested from the 41st year of Shulgi, so close to the end of his reign, through to Ibisin, the second year of Ibisin. So from 2053 to 2026, almost 30 years, 27 years, Shu Enlil is present in the archive. In what he's doing here in this particular archive is that he sent a silver basin to Puzur Era. Along with that, there were many bronze daggers claimed to be the booty of Erbil. So that was treasure recovered from Erbil and then delivered to Puzur Era. Then next we have Kubabtum. And Kubabtum is, her title is Lukur Lugal, so a priestess of the king. Her texts date primarily to around the reign of Shusin, so from 2037 to 2029. For about 8 years, she's present in the text from Drehem. Then Ahan Shibu, the Giri 3 conveyor, for example, delivering a bronze spear to Dayanu Mishar as a recipient and sender and receiver for about 16 years, from Shulgi 44 to Shusin 4, so 2049 to 2033 BC. Next, we have Amur Ili received a shipment of fine leather shoes from Nippur. That text dates to 2026. Now, Amur Ili is a somewhat common name, but if he's indeed the same person who is referred to as Alu Kingia, so a kind of messenger, then he was later in his life a runner or a messenger for the ruler of Marhashi, and his name was Libanuk Shabash, that dated to 2043 BC. So some of these individuals have more common names than others and require disambiguation. Just like Lugal represents many kings, it could very well be that Amur Ili and some of these other named entities have to be disambiguated still. All right, so last but not least, we have Ea Ili, who, at least in this group of texts, is recorded having received various hides to distribute to soldiers. So because this is the Shu archive, he is here working with the leather and shoes and leather and treasure all together. So that he's more or less working at the end of the reign of Shulgi, and his career lasts for about 19 years, again, depending on if these are all representative of the same individual. And during that time, he is a mashkim and a kind of authority at certain points receiving domesticated animals. So you see that while primarily the texts from Draham deal with animal trade, we also get these unique little collections of texts that have to do with when the texts when the hides of animals are processed into shoes, and then also the precious metals and weapons that are traveling in and out of the treasury were collected together in a group of texts. So by looking at the subset of actors in this network, we really boil down who are the primary individuals involved in the administrative practices and, as I said, the hubs and authorities working in Draham during these 30 years. The challenge, of course, when working with ancient texts, and especially those that are from unprovenanced sources, is to see if what you have is representative of the actual administration that took place at that time. From scholarship, we can see that there's an intricate system of trade happening within the archives, and as these commodities are moving from place to place and being dedicated to priestesses and princes and soldiers, they're obviously going around to many different locations. So there's both a spatial and a temporal dimension to this that we're not currently seeing in this graph, but we are looking at applying those to the network. And I think that some of our next steps will be to spatialize and to filter for these entities within a given time frame. So I'd like to end by thanking our fantastic discovery students. And we have not only Yashila and Coleman working with us. This year, we also have Dominique Liu. In the past, we've had many students with us, and all of them can be found on the GitHub repository for this project. We encourage you to return to the notebook if you have any questions. This is currently where the demo concludes, but we hope that this was an informative and enjoyable tutorial, and we look forward to hearing from you. Please don't hesitate to reach out with any questions, and thank you for joining us.